As you're copying this down, I'll kind of review through these properties. The first one is product of powers. This says that if I'm multiplying bases, I'm going to be adding exponents. The thing you got to be careful about is that there's going to be this adjustment of operations, right? That we're not going to be multiplying the exponents together. We're going to be adding the bases. Sorry, adding the exponents together. So x to the m times x to the n is equal to x to the m plus n. Just to give a quick example of this, imagine I had 2 to the third power times 2 to the second power. There's 3 2's here, there's 2 2's here. I'm going to have a total of 5 2's, right? This is 2 times 2 times 2 times 2 times 2, right? This is really going to be 2 to the fifth power, right? And we don't want to say that, oh, 2 to the 3 times 2 to the 2 is equal to 2 to the sixth power, right? We know this isn't true just by, if we were just going through this process, counting how many 2's there are, we see that there's only 5 2's. It's not 6 2's. So we got to kind of remind ourselves that there's a situation when we multiply the exponents, but this is not it. Quotient of powers. If I'm dividing bases, I can subtract exponents. Power of a product. This tells us that I can distribute the exponent through as long as what's inside the parentheses are multiplied together. If what's inside the parentheses are added together, we're kind of stuck. We don't have a nice rule that allows us to distribute the n through and then add the terms. It feels like a natural thing to do, but it's not going to be correct. We can do it with multiplication, but anytime there's addition or subtraction, it just makes properties a little less, a little bit where there's less options for us to work with when there's addition and subtraction involved. Okay, power of a quotient. I can distribute the exponent through my fraction, x to the n times over y to the n. Power of a power. So this is where I can multiply exponents. If I have an exponent directly next to each other, then I can do multiply the exponents. So for instance, if I had 2 to the third squared, now I can multiply. 3 times 2 is 6, which is 2 to the 6th. This I can do. Because what's happening is this is really 2 to the third times 2 to the third. There's 3 2's here, there's 3 2's here. If I add up all the 2's, there's 6 2's. That's why we're able to multiply the exponent here, but not here. Negative exponent. Negative exponents are helpful. It allows us to move variables between numerator and denominator quickly and easily just by changing the sign of the exponent. So if I want my variable that's in the numerator to move down to the denominator, I can just simply change the exponent sign. However, this can only happen if I'm multiplying these terms with others. If this is added to another term, I'm stuck. I can't just move it between numerator and denominator if it's added to another term. Okay, zero exponent says anything raised to 0 power is 1. Doesn't matter what that number is. And the rational exponent allows it to move back and forth between rational and radical form. The rational form is your exponential as a fraction. Radical form means I'm breaking it into a root. So with the denominator, it's going to be to the left of the variable, and then my numerator is going to be to the right of the variable. We did pages 1 through, we did problems 1 through 13 on Friday, and I'll post the key up today, but I like to start on page 3. Okay. Okay, simplify. Express your answer only in positive exponents. So let's go ahead and we know we can distribute these exponents through. So if I distribute, I'm just going to multiply. So I'll multiply the exponents through. So again, there are a lot of ways that you can merge them together. I can distribute through, or I can just look to combine these together first. So multiple ways to get to our final answer. Actually, maybe it's better to just merge these together. These are the same variables here, so I can just rely on this property, right? If I'm multiplying bases, I can simply add the exponents. So if I just focus on the inside here, -2 minus 3, this gives us what? X to the -5, yeah. And then once I have that inside cleaned up, I can move to the numerator or the exponent outside. So now I can do it with these two numbers. Multiply, yeah. If your exponents are directly next to each other, you're going to multiply. And we want to express our answer as positive exponents. So what can I do with this x? Yeah, put it in the denominator. Now, if something is forced to the denominator, the numerator is going to turn into a 1. It's not a 0. It's going to turn into a 1. So this is equal to 1 over x to the 20. Okay, everything this unit is review from before, but we're doing this again because it's such an important topic for next year if you're taking calculus, to be able to be comfortable with these properties of exponents and with logs. So yeah, this is basically our second time through. I know it's been a few years, but at least you've seen everything. Okay, all right, questions for number 1? Okay, so number 2, again, there are a lot of ways that you can go through your steps. Everybody may take a slightly different step, which is fine as long as you're following the rules. And also, every time I do these problems, sometimes I see something, I may do something in a different order. So, so I'm looking here, maybe thinking, all right, everything is being multiplied or divided. So if I can cancel anything out, I can go ahead and cancel out. I can merge variables together. I can cancel out between numerator and denominator. So one quick thing I see is, well, I can just get the 3's to go away, right? There's nothing added or subtracted to the 3 to prevent me from doing that. Okay. Maybe I can start merging the variables together between numerator within each numerator here. So xy cubed, y cubed, I can combine those y's to be what? 2xy to the 6. Notice that if I have variables y to the third times y to the third, right? That's not an exponent next to an exponent. The way I combine it is I got to add those exponents. Okay, denominator, I'll leave it as x squared y to the -4. Okay, so now we're going to look for ways to merge the x's and y's together. The y's I can move up to the top, right? I can either subtract the exponents or I can move the y to the top, make it y to the 4th, and add the exponents. With the x's, there's 1x here, there's 2x's here. If I take away 1x from both, what's left? X in the bottom, right? So again, maybe I'm taking more steps than what you're going to do, but just want to show you everything here. So if I bring the y up to the top, if I want to do it that way, I'm going to be making a change with the exponent, -4 to +4. So the y's are together. I can add the exponent. 6 plus 4 is 10. I can cancel out one of the x's. So I get 2y to the 10th over x. All right, questions so far? Okay, number 3, 2a to the negative 4 over 2a to the negative 4 cubed. I would maybe you see the negative a to the negative 4 and you want to cancel out, but it's inside the parentheses. So why don't we just distribute the parentheses through? And whenever I'm distributing an exponent through, I like to kind of show where my hidden exponents are sitting, so that I know what to do with them. Right? It's nice to have that 2 to the first power, so that we know that okay, if I distribute the 3 through, that it's the exponents that sees each other. 3 times 1, 3 times negative 4. We know 2 to the third is 8. We can make 2 over 8 1/4. And you can subtract the exponents here, or you can move that a to the numerator and then add the exponents. Okay, so you have a lot of options in terms of how you want to follow your, apply your properties here. I made that 2 cubed 8. 2 over 8 is 1/4. Add the exponents. 12 minus 4 is 8. Okay, for number 4 through 6, or maybe even further, we want to apply the special property here. The idea is that if I can get my bases to match, then I can simply rely on my exponents to be set equal to each other. Okay. So the idea is that I can drop the I can drop the bases completely and just focus on my exponents, but only if my bases are the same. So typically, we can make the bases match by bringing a larger number down to a smaller number. So here we have 27 to the x equals 3 to the 2x plus 3. It's easier to bring that 27 down in terms of 3. How can I represent 27 in terms of 3? 3 to the third power. Okay, I haven't changed my 27 to a different value. I've changed the form, but I'm doing that purposely to take advantage of this special property that I have. So I replace this 27 with 3 to the third. And now I can get the bases to match, which means I can drop the bases and just focus my attention on setting the exponents equal to each other. Okay. Combine like terms, subtract 2x, I get 1x, 1x equals 3. Okay, now for number 5, we actually have to do a couple of changes because it's hard to represent 8 in terms of 4, right? 4 to what power is 8? It's not going to be it's not a power of 4, but maybe we can bring both of these numbers down to smaller numbers. What can we use? 2, right? So 8 can be rewritten as 2 to what power? Third. And then 4 can be written as 2 to the second. So if I make that adjustment, then I get the bases to match. I've adjusted the exponents, and now I can just focus on my exponent to help me solve for x. Okay, distribute the 3 through. Combine the x's together, combine the like terms together, set them equal to each other. Solve for x equals 6. Okay, number 6, 3 to the x squared plus 5 equals 6. Let's see if we can just combine like terms and see where that takes us. Feels kind of weird, right? Saying, how can I get the bases to match? So typically we take the larger number down to the smaller number, but in this case, I think we're gonna have to play with this 1 here. What's the same thing as 1? 3 to 0, right? So we're kind of using that special property. We know anything to the 0 power is 1, so kind of using that special property to get my bases to match. And once my bases are matching, I can focus my attention completely to my exponent. So x squared equals 0, solve for x, I'll get 0. That's my answer. Okay, 7 through 9 is a little bit different. We have a little bit more going on than before, but I guess the idea is the same. We still want to get everything in terms of the same base. So what do you think is a number that can be used as a base that can produce 16 and 64? 4, yeah, 4 is good. So I can represent 16 as 4 to the second. Keep the a. 64 is what? 4 to the third. And then keep the exponent that you see there. And then the 64 again on the right side, so 4 to the third. So eventually, we do want to get the bases to match and cancel out and everything, but we do have an additional step that we haven't seen before. We have to find a way to merge this down to just one base. So how can I merge these together? What can I do with the exponents? All right, this is basically a to the m times a to the n is equal to a to the n plus n. I'm going to be able to merge these two bases together by adding exponents. Okay. So once I do that, then now I have a base raised to an exponent equals base raised to an exponent. The bases match. I can now focus exclusively on my exponents and just trying to solve for a that way. Negative 7a equals negative 6. Once I combine like terms, divide both sides by negative 7. Okay, number 8, maybe you don't recognize this 243. But what's if you had to guess, what do you think is a base that will allow all of these to be able to work together? 3. Yeah, 9 is going to be too big to handle 243, but 243 is 3 to the 5th power. Okay, same idea here. Merge the left side together by adding exponents. Now that I have a base equaling a base, I can remove the base and simply look at the exponents and solve for x. Combine like terms, try to get x by itself. All right, number 9. Trying to find a common base that everything can share. What's a common base, you think? 5, yeah. $125 is 5 cubed. 25 is 5 squared. Okay, so now I'm trying to clean up this left side so I can just have it as 1/5 raised to an exponent. All right, so here I'm dividing bases, which means what can I do with the exponents? All right, if I multiply bases, I add exponents. So therefore, if I divide bases, I'm going to do what? Subtract exponents, yeah. Okay, I did a little bit of cleanup as I took the step. So negative 9a minus 6a, at least I'm able to get it down to one base. And now this feels more familiar. I can just get the bases to go away and then solve for a. Okay. Similar process, 10 through 12. I'm going to have you guys try these and I'll work through the same time you guys are working through them. But our goal is the same for all these problems. We're just trying to get the bases to match and then clean up anything that we can do so that it's one base to an exponent equals same base to the exponent, and that way we can move the bases and set the exponents equal.
I'm getting checked out.
Okay, all right, see. Okay, it's a little misleading for number 12. What's the common base that we can have shared between all these 7? Yeah, even the right side can also get that a 7 to show up. 343 is 7 cubed. Five to the 0 is 1, but so is 7 to the 0. So we have that flexibility to use a different base, especially if it's something simple like a 1. So base divided by a base means we can subtract exponents. Now that the bases match, I can make them go away. Just focus on my exponent.
Number 12, wouldn't it just be 3 over 4? Positive 3?
Negative, negative. Yeah, you're right. Should be negative, both negative. Okay, I'd like for us to start and talk about logs, since that's going to be the focus of our units, but we did want to have exponents to start off, since there's that inverse relationship that we want to be able to start establishing. So this is kind of like the anchor, and then we're kind of building logs on top of this. Logs is going to feel a little more abstract, but if we just keep reminding ourselves, it's just the inverse of exponential functions, we can kind of use that to help us navigate through some of the more more of the complex problems. Okay, anybody still need this page? Okay. Okay, page 4. Okay, so a log function is the inverse of an exponential function. So what does that mean? Inverse functions kind of is like a flipped version of the original function. So the way you can get to the inverse function is this. Start off by swapping the x and y. In the second step, you just solve for the new y. So let's say we start off with something that we recognize here, exponential function. Y is equal to b to the x. If I want to find the inverse function, I'm going to start off by swapping the x and y. So I'm going to make this x equals b to the y. And now I want to solve for y. So to solve for y, we have to get it into a form where the y is by itself. And the way we bring the y down is we use something called log functions. Log and exponentials are inverses of each other. So it looks like this. Y is equal to log base b of x. So the special thing about logs, it allows us to bring an exponent down to a place where it's easier to work with rather than stuck up here as an exponent. Okay, so log function is the inverse of an exponential function. Also, visually, an inverse function is going to have this property. It's going to feel like as if you can fold the graph over each other. So an exponential function looks like this. A log function is going to look like this. And they're always going to be kind of have this folded over. It's not reflection over the x-axis, but it's reflection over the diagonal line y equals x. So that's visually, that's what an inverse function is. You're always going to get every order pair is going to be flip-flop. So if there's a 4, 1 here, then there's a 1, 4. If there's a 2, negative 1 here, then there's a negative 1, 2. So every function is going to be flip-flop in terms of their x and y. Okay, so that's the background there. So what we want to be able to go back and forth between logs and exponential form quickly and easily, but it just feels like a bunch of, it just feels very abstract in terms of how do we get from one to the other. So I like to kind of think in terms of going around in a circle. So if I want to get from exponential to log form, I do this. I start with the base, and I say log base b of y is equal to x. So it kind of has that circular motion of working our way through. Same idea here. If I'm trying to get from log form to exponential form, I'll start here as the base, and I'll say b raised to the x is equal to y. So we always start with the base, and from the base, we just kind of work our way in a circle surrounding that equal sign. And that hopefully visually is a way for, so it doesn't feel like you're memorizing, you just kind of think of it in terms of, okay, I'm just kind of working my way around this pattern here. Okay, so let's practice going back and forth between exponential to logs and then from logs to exponential. So I feel like if you can feel like you get that circular relationship with these variables, then it doesn't feel like you're memorizing, you're just kind of following a pattern that you can visualize. Okay, so it says convert from exponential to log form. So that means log form, we want log to show up, right? So we say log base 2, okay? Because that's my base, that's the base of my exponent, but it's also the base of my log. So log base 2, that's going to end up looking like a subscript. And you're going to go in a circle. Log base 2 of 8 is equal to 3. So these are the same things, it's just that we have one in exponential form, one in log form. Okay, so tell me if you can verbalize the steps for number 2. Exponential form to log form, what do we start off with? Good, log base 5 of 1 over 125 is equal to negative 3. Okay, so the way that we say it is log base 5 of 1 over 125 is equal to negative 3. Okay, try that for number 3. See if you can get that exponential form into log form by using that visual circular pattern. Okay, log base what? Log base 81 of 3 is equal to 1/4. Okay. Everybody okay? Exponential to logs. Okay. So now we'll start at logs and we'll work back up to exponential form. Okay. Same idea. Start with a base. Move to the other side. 5 raised to the value is equal to this. So what does this look like? 5 to the power. Yep. Is equal to 25, right? So once you get from log form to exponential form, it becomes a lot more familiar to our eyes, right? 5 squared equals 25, like that makes sense to us, right? But this feels abstract, but we just have to kind of be able to work in this realm, in this world here. But knowing that you're just a minute away from getting to exponential form, so sometimes we like to kind of go back and forth just to kind of get our bearings down a little bit. Okay, so let's try number 5. How can I get this into exponential form? 7 to the negative 3. Yeah, 1 over 343. Okay, so this makes sense to us as well. We know that 7 to the third power is 343. If we flip that back to the denominator, it makes sense. It's 1 over that 7 to the third power. Okay, try number 6. Log form to exponential form. Okay, we're just going to try to get through page 4, and then we can stop. Okay, but I like to get a little bit ahead every day so that I can, by Friday, I can give you a review worksheet since I have to proctor an afternoon exam. Okay, what does number 6 look like? Raised to the, yep, equals 2. Okay, so this makes sense as well because this is really asking for 5th root. So the 5th root of 32 is equal to 2. Right, so I know that, exponential form we're just more comfortable with because that's why we started with exponents. We want to make sure that we are comfortable with that and just understanding that logs is always going to feel more abstract, but we can always get it into something that's more comfortable by just converting it. Okay, common logs. Common log is log base 10. So whenever you see log without any subscript, you can fill that in with a base 10. The reason why we have this hidden base is because we use it so often that we just leave it out, understanding that, okay, if you see log, rather than writing 10 every time, we just know that, okay, that's just, if there's nothing there, then we know it's a 10. So there's a log button on your calculator. Your log button on your calculator is base 10. Okay. Natural log is log base E. So exponential function e to the x. This is very common irrational number that shows up a lot in problems. So we have to. So these are the most common logs, base e and base 10. So e is around 2.72. So it's like an irrational number, much like pi, but it shows up just in a lot of places where we do math. So we also have a shorthand way of writing natural log. Rather than saying log base e, we say natural ln of n. So ln is a shorthand form of writing natural log. So if you see ln, you can always feel free to write log base e if you want to see it in the expanded form. Sometimes it's easier to write it in expanded form because we can see all the different parts. And then there's a button on your calculator that's ln. ln is involving natural log. Okay, so these next examples, we're just practicing getting into the same form as we did above. It's just that getting used to a different way of writing a base. So let's look at number 7. Log of 100 equals 2. What's the hidden base? 10. So if I write it as log base 10 of 100 equals 2, let's get into exponential form now. It's a lot easier once you get that hidden base to reveal itself. So how would you write this in exponential form? Yep, good. So we go in a circle, right? Start with the base, move to the other side, and then come back. 10 to the second power equals 100. That makes sense to us. We know that's true. So my strategy is whenever I see a shorthand form, I always like to rewrite it using the expanded form because visually it's just going to be a lot more familiar to us. So natural log, how can I rewrite this? Log base what? E. So just rewrite the problem, and then you can follow the pattern that we've established a lot easier. So how would you write this in exponential form? Yeah, e raised to the x equals 7. So here, this is not something that is true. This is more of an equation, but we right now we're just asked to write it into a different form. If we want to solve this, we can do that in a later section. Okay, rewrite in log form. Okay, same idea. We know we got to involve logs. So log, what do we say? Log base 10 of 1 over 100 is equal to -2. Okay, but let's practice getting it into shorthand form. How would you write this in shorthand form, abbreviated form? Just drop the what? Drop the base 10 and just say log of 1 over 100 is equal to -2. Same process, get into log form. Let's get log to show up. Log base E of 7.389 is equal to what? Equals 2. Okay, let's practice writing in shorthand form. We'll replace log base E with what? ln, natural log. Okay, it says evaluate the following logarithms. We're going to solve this by hand, okay? We're going to solve this by hand, but we're going to make it look like everything that we've seen above. We don't know what these values are, so just put an equal x to begin the process, okay? Equals x. Okay, so right now this doesn't seem like something that you can easily solve, but I think if we get it into exponential form, it's going to become a lot more obvious. Let's show everything that we know. Log is hiding a what? 10. So let's make it log base 10 of 1 is equal to x. Okay, let's get into exponential form. So let's do that. Start with what? 10 raised to the equals. Okay, so now this, we don't have to use the calculator. We can kind of do a little bit of guess and check. So 10 raised to what power is equal to 1? What do you know about x, about exponential properties? Anything raised to the is equal to 1, right? So we're able to solve this simply by us knowing these properties that are easier to spot in exponential form than it is in log form. So I think we were able to solve this just by getting to exponential form. Okay, so number 12, go ahead and show the x equals x. Everything is showing for us. There's no need to rewrite anything. The base is showing for us already. Okay, so let's get it into exponential form. Start with base 64 raised to the is equal to 8. Okay, this is not going to be a whole number here. What do you think the relationship here? What of 64 is equal to 8? square root, right? Square root of 6 4 is 8, and square root in rational form is 1/2. So we're able to solve these problems just by the properties that we've learned from the previous section. Okay, last one here. Get the equals to x to show up. And then let's get it into exponential form, okay? You'll start off with 5 raised to the x equals 1 over 625. Okay, so first, let's just think about 625, right? 5 raised to what power is 625? 4. But how can I get this good, right? So if I know that 5 to the 4th is 625, I'm almost there, but I do want in the denominator, so I'm going to force this to be a negative exponent. So x equals -4. Good. We got through what I want to get through and more. So we're a little bit ahead, which is good. And that way Friday we can review while I'm not here, and then we'll pick up next week. The test is not going to be until 2 weeks from now. So next week we'll do quote unquote quiz review, but there's no quiz, just to kind of see where we are, and we'll finish up the rest of the unit. Okay, guys, let me check your pages real quick. I just want to check pages 3 and 4.